Hi, and welcome back to the mini series on understanding natural language understanding. This is the last lecture, and we're going to be talking about neurosymbolic AI. This is kind of a new term that means hybrid AI. So actually, it means different things to different people. But normally, when you have a hybrid model that employs such symbolic tools like neural network or statistical models, together with more symbolic approaches like semantic networks or knowledge graphs, then you can say it's a neurosymbolic approach. So in a sense, the suitcase model that we talked about in the previous lecture is also neurosymbolic because we use many different kinds of tools, including lexica and resources together with statistical model. So in our group, we've been working on something like this for many decades now. And we've also been looking at how NLP research is evolving over the years. So now with large language models, we are at the stage where we can very well model semantics. We still have some work to do on narrative understanding, in which that kind of a next level of meaning coding and encoding is required to truly understand what's going on in a narrative. If I talk about what I did this morning, for example, you visualize it. It's kind of you're running a little movie in your head, while a tool like ChatGPT, it just answers or try to reason in a very statistical way. So it's very different, once again, human cognition versus AI cognition. So we explored this and more in some of our papers, including the latest version of SentiGNet. SentiGNet is our own resource for sentiment analysis. And here we look at how we can use conceptual primitives to generalize multi-word expressions like these. And we even try, not really to solve, but at least reduce the symbol grounding problem by coming up with the sort of universal symbolism. And this is trying to solve the symbol grounding problem exactly because we try to model what's really happening for a verb like barter, which again, for a large language model is just an embedding, a vector, but in SentiGNet, it's encoded as a double transfer of ownership. So this really allows the system to better understand what's happening in the operating environment, what's the current state of affairs, based on these conceptual primitives. And this is based on the idea, in fact, that thinking is like acting in an imagined space. If we don't have a way to at least imagine or ground or visualize what's actually happening when I perform an action like this, then it's very difficult to talk about meaning. So if you have a conceptual primitive like this that is somehow grounded, then you can build meaning on top of this. So for example, verbs like get and give can be expressed as a special case of barter, where I replace one of the two arguments with an empty slot. And if I look at different time slots, I can also encode more difficult dynamics like borrowing, where I have a transfer of ownership at t-1, and then later on I return the ownership of the item. This, of course, in case we are talking about physical item. If it's intangible object like information, then the dynamics will be different. And another example could be if I replace one of the two arguments with money, then I can encode always based on barter, the concepts of buying and selling something. And then again, if I use different time steps, renting or leasing something. So this, again, is not solving really the symbol grounding problem, but at least it's an attempt to reduce it. And again, it's an attempt to build a sort of universal symbolism like we have, for example, for mathematical symbols or even musical notes that can counter, first of all, the richness of natural language, the fact that we can express the same concept in possibly infinite ways in English, but also in other languages. So once we have this sort of universal representation that, of course, is only applicable to very basic concepts, conceptual primitives, then the same supposedly applies to any language. So this is one possible attempt to implement neurosymbolic AI. In other cases, as long as I'm trying to emulate the kind of system one, system two, or slow versus fast thinking that we have in our brain, then I can talk about neurosymbolism and also the kind of things that we discussed earlier when we talk about parallel analogy, having the same kind of data represented redundantly in many formats. Another way that people usually talk about neurosymbolic AI is gray box, because it puts together the strength of black box model together with white box. And it's also interesting because it not only focuses on one kind of reasoning like most statistical models do, they just focus mostly on inductive reasoning. Neurosymbolic AI also tries to emulate deductive reasoning, abductive reasoning, common sense reasoning. We'll talk about that later. And so it's not just about learning from example, learning from data, learning in a bottom-up fashion, but also top-down. And that's very much, again, cognitive and human inspired, because in our lives, we don't learn everything by example. I don't learn, for example, that I shouldn't jump out of a window because I tried that before. So it's good that we are looking at mostly sub-symbolic algorithms nowadays, but we need to look at more than that if we want to really get a step closer to AGI. And that's why I believe, and many others believe, that neurosymbolic AI is really the future of AI. Another way to see neurosymbolism is using the funny metaphor of magic. So science is magic that works. So if we use magic as an analogy for AI models, then subsymbolic AI would be black magic, because it's very powerful, but we don't have much control over it. While symbolic AI, like neural semantic networks or knowledge graphs, are more like white magic, very controllable, easy to control, easy to understand, but not as powerful. In this analogy, neurosymbolic AI would be a mix of both, where I try to get the best of both worlds. And how can this be done? Again, and there are different ways of doing this, and we are experimenting with them. In this example, we use ScientificNet, the common sense knowledge that we have in ScientificNet, a knowledge base, to inject extra information into a neural network, specifically a graph convolutional network. The opposite is also fine. You can use a subsymbolic approach to build a graph, a knowledge graph, in which, for example, you use some training data to understand all the possible ways that I can express a concept like buying in English, and then you don't use that directly for classification, but in fact, you use it for building a knowledge graph like this, which in our case is also hierarchical. So you have a lot of name entities at the top, which are expressed in terms of using is-a links, in terms of concepts, words, and multi-word expressions that are then linked to conceptual primitives, which are in turn linked to super primitives. So a super primitive is a very general conceptual primitive that cannot be further generalized. And so this allows us to explain concepts in the same way as you do, for example, in physics, when you explain speed in terms of distance and space. So this is, again, to counter the limitations of word embeddings, which are, as we discussed in past lectures, are very good for calculating, for example, the similarity between things. But again, if I don't ground meaning somewhere, I can only tell what's similar to what, but I can't answer things like what is what, right? And this is a the problem that has always been there since we've been only been working at the surface level on text and not really on meaning. And it's the same problem that you face when you pick up an English dictionary and things are defined in terms of other things and vice versa. So you have this kind of semantic loops that if you don't ground them anywhere, then it's very hard to build a truly intelligent system. And this goes back to the discussions that people working on semiotics had. So the difference between the signifier and the signified. The problem with language is that we basically learned to associate meaning to language by brute force. Because if you take a word like lion, there's nothing in these four words that resembles a lion, nothing. So we need to make this connection in our brain by brute force. That's what we did in the first years of our life. And the same kind of thing needs to happen in machines if we want them to truly understand the meaning of things. So far, we've only been working at signifier level. Another problem is that when you just work at this surface level, you tend to have no common sense. Why? Because a large language model really never had the chance to live, to see, and to feel the real world. And common sense knowledge is much more ubiquitous than we think. It's about affordances, size, compositionality, typicality, and many more things that we do almost automatically without even realizing. So if I tell you something like this, I saw the Colosseum flying from Rome to Genoa, we don't think twice about the possible meanings of this, but potentially it could be that it was the Colosseum that was flying from Rome to Genoa. And we didn't think about it for a second because it's so natural for us to know, to have enough common sense to know that the Colosseum couldn't be flying. And so it was me that was flying and saw the Colosseum. And you may say, okay, this, because this is a special sentence, a special case, but actually we use common sense even in the simplest sentences. In a sentence like this, we don't think twice about the meaning. We know that this means that the speaker saw a kid with a cat. So potentially the preposition with could also mean that I saw a kid while I was holding a cat, right? It's very uncanny to say it like that, but it could be a possibility. As well as if I don't have enough common sense to tell me that the cat is not an instrument, it may mean that I use the cat to see the kid. And unfortunately, there are many more horrific options, like, as you know, so also have other meanings. And I can go on like this, on and on, to just to say that we use common sense much more than we realize, but an AI model in general that doesn't have common sense really needs to think about all the possible meaning that a sentence like this could have. So with this in mind and with the idea of building neurosymbolic models, we also built our own common sense knowledge base. It's called PrimeNet. It's freely available, and it's a hierarchical common sense knowledge base so that you have that a conceptual primitive like tool will have a lot of concepts like hammer, and then all different kinds of hammer as entity. We use different kinds of relationship, but mostly the is-a relationship to build these hierarchies. And this is also trying to do the symbol grounding problem that we were mentioning before. So for example, we have words like build that are generalized into the conceptual primitive generate, which also has a definition like this. So it's, again, generate is not just an embedding, but it tells me that what's the current state of affairs of my operating environment. It means that something that wasn't there, didn't exist before, now exists because it has been generated. And again, this is also useful to counter the richness of natural language processing, which can be very important task to do, for example, for human-robot interaction. So there are countless, if not infinite, ways to express a concept like this, that the temperature of a device went up. So if I have something that can generalize this into a more canonical form, that can be very useful for human-computer interaction or even human-robot interaction. So we tested this PrimeNet on different data sets, and you can read more information about this in the book or on the paper. And the goal, again, is to implement this kind of system one, system two, or fast thinking versus slow thinking together with the usage of large language models. And we tested PrimeNet also on multimodal settings in which we had images and we had to make common sense based decisions. And also, we're also always working on evaluation, how to evaluate different kinds of reasoning for neurosymbolic systems, but also for large language models. So I want to conclude talking a bit about adoption. So today, of course, an AI expert is like the man or the woman of the moment. Yeah, there are also risks, as we discussed in the second lecture about job displacement. But ultimately, what's happening, especially in advanced economies, is that we need more AI experts. So we put together steps for adoption of AI. And also the big question here is when it makes sense for me to build my own AI model. So if I'm just using AI as a black box or as a service, it's totally fine for many applications. So it's okay to use an API, for example, Cintiq APIs or even ChatGPT, and build on top of that. The benefit from building my own AI model comes in the fact that it's an interpretable. So if I can interpret my model, then I can also do things like error analysis and ablation studies. And this is also very useful for explainability, because if my explainability is based on the interpretability of the system, then I can trust it much more. And that's exactly the next phase of AI is trustable AI, whereby I'm not just happy to have any explanation that could be like a generated explanation, but I also test how good are these explanations in terms of utility, how useful the explanations are, how robust are these explanations. If I keep asking, do I get the same explanation or not? And finally, faithfulness. Is it truly how the system came up with this output? Last but not least is an AI that is human-centered, that has a human in the loop, and it's also interactive. So, for example, if after asking for explanations, I realize that I don't like the output because maybe my model has used a part of the training data that I don't like or I don't trust, I can ask the system to remove that part of the training data and recalculate the output based on the new data. So there's still a lot to do in terms of the challenges that we face in AI and data science as well. One is privacy. So remember, when we talk about vector spaces, actually now some scientists discovered that the geometry of vector spaces is kind of universal. So even after you represent a data point in a vector space and you delete the data, you can still recover some of this data by using another embedding. So if I use some special, my own personal embeddings to build a vector space, I can still use a more general model like Word2Vec to recover some of the original data. So this, of course, is a problem for privacy, because in the past, to ensure privacy, we would just for example, represent patients as data point in a multidimensional vector space and then delete the original data. But now apparently that's not enough anymore. There's also a problem of comprehensiveness of the data. Some of the companies I work with actually have this problem more often than not. So they tend to forget that in order for the system to really understand the problem, they need to have access to all kinds of data, not just about one product, but possibly all the products that the company is working with, and also their competitors, and also similar products. And not just the products in general, but the specific aspects. Remember when we talk about aspect extraction. And in that sense, in that context, it's also important to talk about balancedness. This is also another common error that many companies do. They tend to have a lot of data, but this data sometimes is skewed. Like if we talk about polarity, they tend to have maybe 80% of negative reviews and only 20% positive. So obviously, if you use this for training, your system will be skewed towards negativity. So it's important to know what's the ideal case. So in the case I'm collecting, let's say, 1,000 tweets from relevant tweets from the web, then ideally I should have half of it that is objective and half of it that is subjective, and of this half should be positive, half should be negative. And if I have 5 aspects, then this should be also equally distributed. Of course, having something like this, it's impossible, but knowing at least what's the ideal case and trying to get as close to it as possible, it's important. Last but not least, also bias. That's something that we have also been studying quite a lot recently. And it's important to recognize bias and try to reduce it as much as possible, especially in vision language models, but also in large language models. So what's the future of AI and society and work? This is something that we can discuss, but ultimately anything that can be automated in terms of written production that is not creative and doesn't have so much of the human factor can potentially be replaced. So my recommendation is really to focus on those jobs or those aspects of the jobs that require more human touch. And the jobs of the future definitely are those that use AI to increase the kind of interconnection that one can have, for example, with their teammates or their clients. So, for example, until now, maybe a financial advisor has been using some DIY tools to try to guess where the market is going, but now it can use explainable AI to make more informed decisions and then ask for explanation so that it can also better explain to their clients what's happening and why some decisions should be taken. So personally, I have a more optimistic view of what's happening next, but I always see the human in the loop because AI has a lot of strengths, but we humans also have a lot of strengths because AI by itself doesn't really have any incentive or any reason to do anything. So the way we use AI can really enhance our capabilities, our productivity, and our society ultimately. And there's maybe also some things that we can learn from AI, like it's happening in some cases where Go players are getting inspired by the way DeepMind is playing Go, or even, as I mentioned, some financial advisors can use AI to take better decisions that otherwise would be a bit irrational because they are free from emotions in some cases. So that's really about it for the AI part. I want to conclude in the last few slides, talk about one possible application of AI, which is AXA, or affective computing and sentiment analysis. These are all subset of each other. Sentiment analysis is mostly recognized as polarity detection, a binary classification between positive and negative. Affective computing is more about emotion, and this is also a subset of AI. And I think this can be interesting in the years to come because so far we've been focusing a lot on IQ, but there's so much more that needs to be done in terms of EQ. And EQ is really important for intelligence in general, so much that, for example, Marvin Minsky was wondering whether machines can be intelligent without any emotions. So emotions definitely play an important part in our reasoning capabilities. The studies on emotions, they date back in the 1872 from since Charles Darwin wrote about the evolution of species, and after that many more psychologists have been looking at emotion categorization models like the OCC model or the Ekman emotion model or Plutchik wheel of emotion. And we also have our own emotion model called the hourglass of emotion that recently has been revisited. And there's been a lot of things that we have changed. We have used better colors to define emotions like disgust and sadness, but also we've been looking at using, for example, better colors for positive emotions. And so warm colors for positive emotion and cold colors for negative ones, and also make sure that there was the right association between antithetic emotions. So in the past model, we had that fear was facing anger, but fear and anger are not really polar opposite. So we changed that with anger versus calmness and fear versus eagerness. And eagerness and calmness specifically are emotions that were missing before, and they are actually missing from most emotion categorization models. So this is something that we also came up with after some discussion with Andrew Ortoni. And finally, we also have moral or self-conscious emotions in the hourglass on the dimension of pleasantness versus disgust, depending on whether these are directed at ourselves or towards others. Another thing that is very different from other emotion categorization model is the absence of surprise. In many models, surprise is one of those positive emotions, but actually surprise, well, some claim that surprise is not even an emotion like Andrew or Tony, but from a point of view of polarity, yes, surprise by itself is neither positive or negative. It's only when paired with another emotion that it becomes either positive or negative. So based on emotions through the hourglass, we can also calculate polarity and other combined emotions. And there was a problem with the polarity, the formula for calculating polarity earlier. So we also updated that, and now this is the new formula that works much better for calculating polarity based on extracted emotions. So we've gone a long way from the time where we were just using rules for sentiment analysis, and these were the times where Janice Wiebe started actually the field of sentiment analysis from psychology, and also the book on affective computing by Rosalind Picard. And later on, we started having more statistical methods associated with polarity detection, but also interesting ideas about how to build an intelligent machine. And later on, we've been focusing more and more on explainability, and this is also important as we discuss. And we have been building a lot of lexica, common sense knowledge bases, and started the field of affective computing and sentiment analysis. And based on explainability, then recently many more works came out about personalization. And this comes from the fact that even the same sentence can be positive or negative to different people depending on their personality. So personalization is really the next step after explainability. And then last but not least, we have predictive sentiment analysis. So once we have personalization and explainability, we can use these to do a sort of user profiling based on different demographic groups or different users, and even be able to forecast how they will feel if a certain event happens or if a certain product comes out. So based on this, we are also moving towards more cognitive modeling and individualized cognitive simulations, and we use different tools not to just calculate explicit sentiment, but also implicit. And how can we do this? There are several ways, including the use of metaphors. So when we look at metaphor understanding, we can do a bit like the word association test of 007, where this is actually a psychological test, but it's also featured in 007. We're given a word, the other person has to say the first word that comes to mind. So by doing this test, we can understand the conceptual mappings of people and how they associate different concepts to other concepts. So one famous thing that 007 says is that he associates heart to target, while most people will probably say love or affection. So this is very useful for individualized cognitive simulations. So this is what we do together with standard affective computing methods and neurosymbolic AI. We also look a lot at cognitive science. So this interaction of different fields is also what we call our own approach, scientific computing. That's why we are called Scientific Team and Scientific Net. So I want to conclude with some possible outlets for collaboration. These are the 7 main research umbrellas that we're currently focusing on. As I mentioned, we work a lot on explainability, of course, with special focus on sentiment analysis. We work also on personalization, different levels of personalization, starting from subjectivity, subjective preferences, but also personality, ideology, and so on. We work mostly on text, but we also focus on other modalities like speech and multimodal analysis of facial expressions and videos. Recently, a lot of work on multimodal sarcasm detection, for example. And what's interesting there is also how to fuse different modalities. We've been working on different languages. This in this specific work, we used a rotation matrix to basically overlap 2 different representations of 2 different languages using some concrete anchor concepts to basically fuse these 2 representations, and then in the new shared representation we can study the semantic variations between concepts. So this is also useful, for example, to study cultural differences embedded in different languages. We also explore multitask learning, as I mentioned earlier when we were talking about sarcasm. In some cases, it's good to use a multitask learning architecture, for example, for sarcasm detection plus sentiment analysis. And a lot of works on so-called empathetic dialogue systems that can also measure how the emotions of the user change over time throughout the conversation. And finally, as mentioned, predictive sentiment analysis is also an important research umbrella that encapsulates many of the other research umbrellas. So on top of these research umbrellas, we also have a lot of active projects in which we use explainable AI for different practical applications, from business intelligence, which is the prime application of explainable sentiment analysis, and then climate resilience. We have several works on sustainable investment and corporate sustainability, greenwashing detections, and also using metaphors to better understand topics related to ESG or sustainability. Being in education, of course, we also use AI for understanding how the students feel throughout their learning process. We have several works on AI for science. This is a picture that I used earlier when I was talking about task decomposition. So this is our AI scientist that is using different large language models to come up with new scientific hypotheses. And we also use our tools for healthcare, specifically mental health care. A lot of works recently about explainable depression detection and suicidal ideation detection, and also XAI for online safety, so to counter phenomena like cyber harassment, cyberbullying, toxicity, and sexism. And finally, also working a lot on explainable AI for finance. So in this case, we look at both technical analysis and sentiment analysis to make more informed decisions. So that's all. In the last few slides, I just want to talk about some of the more recent work on foundation models. So we put together these umbrellas and these projects to build what we call the Human Behavior Atlas. So this is a foundation model specifically for affective computing human behavior. So we put together a lot of training data sets from various tasks and also taking as input text, speech, and even like different positions of the body, and then use this for several downstream tasks from emotion detection to depression detection, anxiety detection, and so on. So if you're interested, you can check this out. We also have some code available on our GitHub. And this is actually making us realize that there are even more questions to be answered, because then we started looking at some of these data sets and we started wondering how much can we trust these labels, these emotion labels, because in some cases, many of the data sets available in affective computing are actually enacted emotions. So which tools can we use to make sure that we are actually working with the correct emotion? This is also an open question, an open debate in affective computing research, but also in psychology. So that's all I had to share. And here you have some more links to this Department of IEEE Intelligent Systems on AXA and these other open special section on cognitive computation. We also have a book series on this topic. You can check that out. But ultimately, if you want to keep yourself updated with with what we're doing, you can just follow us on YouTube, where we usually post some short videos, and we also have a lot of downloads on our downloads page, CenticNet, AffectiveSpace, PrimeNet in many different languages, a lot of codes on our GitHub. These open source large language models for Southeast Asian languages. MetaPro is our tool for metaphor understanding. And finally, Centric APIs that can do many of the things that we discussed earlier in the suitcase model in a very easy and analytical way. So given an input, you can get an output, very formatted output in an Excel file about emotion, polarity, sarcasm, depression, and so on. And these can also be visualized in a nice user interface. So these are all tools that are freely available for research, and you can also use for your assignment. So that's it for now. Thanks for your attention. I hope you enjoyed this mini course. If you have any questions, once again, you can ask me, or you can leave any comment, and I'll see you next time. Ciao.